So if we look at number 57, energy is transferred from sunlight photosynthesis reaction, in which carbon dioxide and water vapor combine to produce sugar, C6H12O6, and release oxygen. The amount of energy is 2.82 times 10 to the third kilojoules per mole of sugar formed. So this one is endothermic. This is energy is absorbed in this particular reaction. So the reaction is plants take CO2 and water and combine it. So this is the reverse of combustion, C6H12O6 and O2. Normally we do the reverse. The reverse is we burn the sugar with oxygen to form CO2 and water. CO2 is a gas, H2O is a liquid. In this case, I'll just balance this quick. I think this should be balanced here. All right, the amount of energy that's transferred here is 2.82 times 10 to the third kilojoules. So delta H is equal to 2.82 times 10 to the third kilojoules. Now, from the wording of the problem, it's kind of hard to get, but basically this is an endothermic. Endothermic means it consumes energy. And so either we write the energy as a reactant over here, or we write it over here as a plus, like that. Now, this is delta sub R. Delta sub R means that this is the amount of energy for the reaction as written. And so when we look at the mole ratios, it would be 2.82 times 10 to the third kilojoules of energy for every 6 moles of CO2, etc. Or over here, it would be 2.82 times 10 to the third kilojoules for every mole of sugar that's synthesized here or produced per 1 mole. And so it's for the reaction as written. So we look at the stoichiometric coefficients here, and then we can generate energy conversion factors. That means we can go from moles to kilojoules, or flip this over and go from kilojoules to moles for any of the reactants written in the equation. So we need to know is that, energy that consumed or energy produced. When gaseous nitrogen reacts with gaseous oxygen to form nitrogen dioxide gas, 66.4 kilojoules of energy is transferred for each mole of nitrogen that reacts. This is weird. Is that energy released or energy consumed? Consumed?
Released. Because usually when oxygen reacts with something, it produces something much more stable. So it's released.
Yeah, normally it could be exothermic. It's not so clear from the wording. Usually we don't word it transfer. Transfer is a very unusual word to use for this. Normally, instead of transfer, we say that energy is consumed or energy is produced. And so it's stated in an awkward way. All these say energy is transferred. This one's more straightforward. 61. The reaction in the oxyacetylene torch is highly exothermic. So exothermic means it's released. Releasing 1.31 times 10 to the third kilojoules of heat to the environment for every mole of acetylene burned. So this would be exothermic. Carbon dioxide gas reacts with hydrogen gas to form carbon monoxide gas and steam in 41.2 kilojoules of energy. So this is how much heat or energy is produced or formed. It's fine, so that's exothermic. And the others are a bit weird. And so let's do some stoichiometry here. 63, quicklime, the common name for calcium oxide, CaO, is made by heating limestone, calcium carbonate, in slowly rotating kilns, which are a type of oven. This is the reaction that the Romans did. They took calcium carbonate and heated it in their kilns, to make quicklime or calcium oxide. Quicklime or calcium oxide is used in the manufacture of cement, old concrete together. The reaction is calcium carbonate plus 178. So this is endothermic. We need to add this much heat to get this to go. What quantity of energy in kilojoules is required to decompose 5.80 kilograms of limestone? And so we'll just look at the setup. So we're going to go from kilograms of limestone or calcium carbonate to grams of calcium carbonate. Grams of calcium carbonate to moles of calcium carbonate, moles of calcium carbonate to kilojoules. And so the mole ratio here is 178 kilojoules per 1 mole of calcium carbonate. What mass in grams of hydrogen has to react to transfer 71.9 kilojoules of energy from the reaction? Transfer, there they go again with transfer. This is to produce 71.9 kilojoules. So heat is a product, so we're going to make 71.9. If we burn 2 moles of hydrogen, we get 484 kilojoules. We only want 71.9 kilojoules, so we're going to burn a lot less. And so we're going to go from kilojoules to moles of hydrogen. It's 2 moles of hydrogen for every 484 kilojoules. And then moles of hydrogen to grams of hydrogen. So we'll do that. Quicklime produced in question 63 is frequently converted to calcium hydroxide, sometimes called slate lime, by exothermic reaction with water. So again, this is exothermic, so it's produced as a product. Calcium oxide plus water yields calcium hydroxide plus 65.3 kilojoules. What mass in grams of quicklime was processed in a reaction that transferred 291 kilojoules of energy? So this one, 291 kilojoules is more than that, so we need more than a mole. And so it's kilojoules to moles of calcium oxide and moles to grams. So we'll do a specific example coming up. We're going to do number 67 here. What mass in grams of octane, a component of gasoline, would you have to burn in your car to transfer 9.48 times 10 to the 5th kilojoules of energy? So here they give us a delta H. And the delta H is negative, which means energy is released or energy is produced. And so this is a delta HR. The R is for this. So this is the amount of energy that we get by burning 2 moles of octane, because that's the reaction as written. So let's go ahead and do this one here. So we want, now the sign convention this is an exothermic reaction. So delta H sub R is equal to minus 1.09 times 10 to the 4th kilojoules. And so there's 2 ways that we could write this. One is we could leave the negative sign in there. Or 2, we can get rid of the negative sign and just say 1.09 times 10 to the 4th kilojoules released. The sign just tells us, was the energy lost to the surroundings, or was the energy consumed from the surrounding? And so in this case, it's lost or released. And so I'll just say 1.09 times 10 to the 4th kilojoules released. Okay, so that means how we handle this. It says we need to transfer 9.48 times 10 to the 5th kilojoules. needed. And so there are two ways of dealing with this and keeping consistent with the sign. The first way we can do is we can just say 9.48 times 10 to the fifth kilojoules needed. And then we're going to say that we have 2 moles of octane, C8H18, for every 1.09 times 10 to the fourth kilojoules released. And then we'll convert this to grams. And so we calculate the molar mass for octane. Or if you do a lot of these, then you might skip the molar mass calculation and just look it up. I'll just look it up. Octane. Octane has a lot of meanings. All right. Octane, boy, sometimes looking it up is slower. 114.23. 114.23 grams. Octane's not so bad because carbon's 1201. That's one of those ones you might have memorized. Hydrogen's 101. So it's not terrible to calculate it. All right, so this should give us grams of octane in order to get this much heat. The other way that we could do this is we change the sign on this. This is the 9.48 times 10 to the fifth kilojoules negative. Negative meaning it has to be released from the reaction. And the reaction releases how much? 2 moles of C8H18 for every negative 1.09 times 10 to the fourth kilojoules. Here I don't need to put release because the negative sign tells me that. A positive sign means it's going to be consumed. Negative sign means it will be produced. Times 114.23 grams of C8H18 per mole of C8H18. Now, this one, whatever we do, we have to be consistent with the sign. So if we don't add a word, released or consumed, then we got to make sure that we keep track of the sign so that we don't end up with negative grams. You know, negative grams doesn't mean anything. And so we're going to either keep them both positive and add the word there, or leave the sign and recalculate it based on the direction of transfer. Okay. See any other delta H? The same thing here. Delta H negative 75.8 exothermic. Here's a positive. Delta H is positive 41.2. This would be endothermic. It would be a reactant in this case. So heat is a reactant. Heat is a product here. Heat is a product here. Here, heat's a product, but they change the sign and write it on the other side of the equation. So different ways of doing that. Okay, are you okay with this? The heat? Do you want to do another problem with the heat or another problem? 76. How much energy is required to decompose 1.42 grams of KClO3 according to the following equation? 2 KClO3 solids yields 2 KCl plus 3 O2. All right. What is the name of KClO3?
Calcium chloride.
Yeah. And it turns out when you heat potassium chlorate, it can decompose like calcium carbonate. Calcium carbonate decomposed into calcium oxide plus CO2 gas, but KClO3 decomposes into KCl and O2 gas, not CO2 gas. All right, delta H sub R for this is equal to 89.5 kilojoules, or is equal to 89.5 kilojoules, consumed, not produced. And so here we don't need to change the sign to anything. So we're going to go from grams of A, 1.42 grams of KClO3, potassium chlorate, to moles of KClO3. This one I'll have to look at. KClO3. Hopefully it comes up. It did. So the molar mass of KClO3 is 122.55 grams per mole. So 1 mole of KClO3 potassium chlorate weighs 122.55 grams. The grams of KClO3 cancel, that leaves us with moles of KClO3. Once I have moles of KClO3, then I'm going to use this as a conversion factor. 89.5 kilojoules of heat is consumed for every how many moles of KClO3 as written? 2 moles of KClO3. So this is going to be per 2 moles of KClO3. And so the moles of KClO3 cancel, and that should leave us with how many kilojoules of heat I have to add to get this to decompose.
Professor, for the KClO3, you said it's a solid, but does it just not matter if it's aqueous in this situation?
Well, there's no water present in this particular one, and you have to heat it up so hot that it would evaporate the water if there was water present.
Okay.
But normally KClO3 is soluble, and so
Yeah.
is aqueous. So if there's water present, you'd write AQ, or
So when we're doing like the solubility from like the other reactions that will probably be on the test, we'll just assume there's water usually, and we'll assume there's not water if we're doing this heated stuff.
Yeah, this one has to be heated to a very high temperature. And so, I mean, there could be water. It could be. The first thing is you're going to boil off all the water and be left with the salt, and then you're going to heat up the salt until it decomposes. A lot of salts will melt, and so, but some salts will decompose, like chlorate. Chlorates aren't very stable, pretty reactive.
Without water, it would be solid if it's a salt.
Yeah, like table salt. Table salt is very soluble, but you could have solid table salt. You can sprinkle it on French fries. You can try to heat it up. When you heat up table salt, it doesn't decompose. It would melt. That's because, sodium ions aren't a very good oxidizer. Chloride ions are stable. They don't want to lose. They're not a very good reducer. They want to hold on to electrons. But in something like this, you can see that this isn't going to be so happy because chlorine has a +5, oxygen's -2. So if you get it hot enough, so far they're living okay. The oxygen is -2, the chlorine's +5. But if you start heating it up, things can happen. When you heat it up, the chlorine can take the electrons actually from oxygen. In fact, that's what happens here. The chlorine goes from +5 to -1, so it gains a lot of electrons. Well, the oxygen went from -2 to 0, so it lost the electrons in this particular case. And so when you heat it up, it form that, which is a more stable mixture than this. KClO3 is not inherently stable. It's a good oxidizer. KClO3 is what I used in the sugar rocket. Do you remember that? Pure rocket. This was the oxidizer I used. Chlorine has a hard time taking the electrons from oxygen. You need very high temperatures for that. But if you don't need high temperatures to take from sugar. Sugar electrons are easy to take. And so let's go ahead and calculate this. It's going to be 1.42 divided by 122.55 times 89.5, 0.037. kilojoules. That's not much. 1.04 kilojoules. All right, so those are the two typical problems that you're going to run into. One, where you're given an amount and you have to calculate the energy. The other, when you're given energy and you have to calculate the amount. Okay, in stoichiometry, we're going to have a number of more challenging problems here. And the more challenging problems involve percentages here. So basically, when we're dealing with percentages, we add a couple more branches. So this is the mass of A. We go from mass of A to moles of A. Moles of A to moles of B. And then moles of B to mass of B. But when we're doing this stoichiometry like this is pure A, and this is pure B. So we might have like this. We might have a certain number of grams of octane, and we combust it in air. And so we might go, okay, I have the mass of octane to moles of octane. And then I want to figure out how much oxygen I need. So I go from moles of octane to moles of oxygen. And then from moles of oxygen, I can go to grams of oxygen. But is air pure oxygen? No, air is like 20%, a little more than 20. It's like 22% by mass of oxygen. And so what I could do is I could do one extra step here. Rather than stopping at mass of oxygen, I could go to mass of air. And that would be the mass of B mixture. So let's say I calculate I need 22 grams of oxygen. Well, that would be 100 grams of air. Because air is about 22% by mass oxygen. Or I could start off with air. If I start off with air, I have mass of, air contains oxygen, mass of an oxygen mixture, and then figure out how much pure oxygen I have in that sample of air. And so I could have a mass of A, not pure, but A mixture. And go here. So, or back. Vice versa. Either way. It depends on the problem. And so let's take a look at problem number 77 here. A phosphate rock core yields rock. The rock is going to be a mixture. And this rock mixture consists of 79.4% calcium phosphate. So number 77. In this case, this rock mixture contains 79.4% calcium phosphate. What's the formula for calcium phosphate? What's the charge on phosphate?
-2.
Well, -3. So I'm just going to do Ca3PO4. The charge on calcium, 2. So Ca3PO4 2. What this means is this is by mass. And so what this means is I'm going to have 79.4 grams of pure calcium phosphate for every 100 grams of what? Of mixture. But this mixture we call rock. So for every 100 grams of rock, I'll have 79.4 grams of calcium phosphate and like 20.6 grams of other stuff. This is stoichiometry using mixtures. Calcium phosphate is the raw material used in preparing calcium dihydrogen phosphate. That's what this is called, dihydrogen phosphate. A fertilizer known as superphosphate. The rock is made to react with sulfuric acid according to the equation here. It's kind of a double replacement equation. It's a little bit more complicated. What is the smallest possible mass of rock in kilograms that must be processed to yield 0.500 tons of fertilizer? So we're starting off at 0.500 tons of fertilizer. The fertilizer is calcium dihydrogen phosphate, so CaH2PO4 2. So what we're going to do is we're going to go from tons. Do you know the conversion from tons to? You don't need to know the conversion. It's 2,000 pounds in a ton. And so we have pounds of fertilizer, 1,000 pounds of fertilizer. Do you know the conversion from pounds to grams? You don't have to have it memorized. You might. It's 453.6 grams per pound.
Mm-hmm.
And so now we're going to have grams of fertilizer, grams of calcium dihydrogen phosphate. Okay, now we'll have to go to what? Moles. And I wonder if superphosphate, the molar mass is here. Let me see. Oh, it is. That saves me. Oh, it isn't. Not there. All right. Well, you hit that point where it's not worth that. And so we'll just calculate it. Wanted to avoid calculating it, but stop. So calcium's 40.08. How many hydrogens do I have? 2 times 2. So 2 times 2, 4 hydrogens. 2 of these. 4 hydrogens, 404. How many phosphoruses do I have? 2. It's 30.97 times 2. How many oxygens? 8. That would be 8 times 16.00. So I did one of these in my head with hydrogen. So I'm going to get 40.08 plus 4.04 plus 60, 30 times 2 times 30.97 plus 8 times 16. 234.06. Is that what you guys got? So 1 mole of calcium dihydrogen phosphate weighs 234.06 grams. Okay, the calcium dihydrogen phosphate is going to be synthesized from calcium phosphate. And so the mole ratio here is a 1-to-1 mole ratio. So 1 mole of calcium phosphate for every 1 mole of calcium dihydrogen phosphate. One. And then I'm going to go to grams of calcium phosphate. Let's see, grams, the mole mass of calcium phosphate online. Let's try it. And it is here. No. No. CRC would have it. Let's see if Chem has it. It does. Chem has it. 310.18. So I saved a little bit of work. 310.18 grams. C3PO42 per mole. But I'm not done there yet, because they're not asking how many grams of pure calcium phosphate I need. They're asking how many grams of rock I need. So I'm going to have to use this one, because for every 100 grams of rock, I only have 79.4 grams of calcium phosphate. And so that should give it to us. Let's try 0.5 times 2,000 times 453.6 divided by 234.06 times 310.18 times 100 divided by 79.4. Oh, I get 757,000 grams, but they're not asking us grams, and they're not asking us for tons. Do you know what they're asking us for? Let's take a look. They're asking us for kilograms. So I need to do one more step here. For every kilogram, there's 1,000 grams. And so this is going to come out to 757.0 kilograms of rock, or 757 kilograms of rock. All right, so there's a stoichiometry problem with an extra step for the percentage. Let's look at 78. Carborundum silicon carbide is widely used as abrasive in industrial grinding wheels. It is prepared by the reaction of sand, SiO2, with the carbon in coke. Coke is not pure carbon. What mass in kilograms of carborundum can be prepared from 727 kilograms of coke? That is 88.9% carbon. And so this is where we start off with grams of A to moles of A, moles of A to moles of B, moles of B to grams of B, grams of B to grams of B mixture. And so what we have here. But in this particular problem, we're going to start off with A mixture. And so in number 78, we have 727 kilograms of carbon mixture called coke. And it's only 88.9% pure carbon. So it's 88 point, well, actually, let's go to grams. So kilograms, 1,000 grams per kilogram. And so we have grams of coke. And then it's going to be 88.9 grams of pure carbon for every 100 grams of coke. And so we're going from mass of A mixture to mass of A pure. Once we have mass of A here, then we can go to moles of A, and then to moles of B, and then to mass of B. And so we want mass of silicon carbide at the end. So we go from kilograms of coke to grams of coke, grams of coke to grams of carbon to moles of carbon to moles of silicon carbide, and then to grams of silicon carbide, and finally to kilograms of silicon carbide. Is that clear for this? So it's at the beginning this time. So we just go, etc. Do you want me to finish it, or you haven't? Finish it or move on? Finish it? Okay. So a carbon is 1 mole of carbon weighs 12.01 grams. And so we have kilograms of mixture to grams of mixture, grams of mixture to grams of pure A, which is carbon, grams of carbon to moles of carbon, then moles of carbon to moles of silicon carbide. And so it's a 3-to-1 mixture here. So 1 mole of silicon carbide for every 3 moles of carbon. And then we need to go from moles of silicon carbide to grams. Silicon is 28.09. Silicon's 2809, and then carbon's 1201. And so this is going to be 40.10. Okay, and then finally, they want it in kilograms. And so 1 kilogram is equivalent to 1,000 grams. And this should give it to us here. Let's try this. 727 times 1,000. It goes to 727,000 grams of mixture times 88.9 divided by 100, which is 646,303 grams of pure carbon divided by 12.01. Oops. Fifty-three thousand 813 moles carbon divided by 3. Is 17,937 moles of silicon carbide times 40.1. It's 719,000 grams of silicon carbide divided by 1,000. So I'm going to get 719.3 kilograms of silicon carbide, or 719 kilograms. So that's a challenge problem when we're dealing with a mixture. There's one more type of problem when we deal with mixture. Tell you what that is. This one, number 87. We'll do 87. 87, a student was given a 1.6240 gram sample of a mixture. So this, you get some kind of mixture here where it's 1.6240 grams of mixture. They tell us what's in the mixture. It's sodium nitrate. What's the formula for sodium nitrate?
NaNO3.
NaNO3. And sodium chloride. What's the formula for sodium chloride?
NaCl.
NaCl. They take this mixture and dissolve it in water. And then they react it with silver nitrate. What's the formula for silver nitrate? AgNO3. Sodium nitrate plus silver nitrate makes what? Sodium nitrate plus silver nitrate makes same thing, sodium nitrate and silver nitrate. So there's no reaction. Sodium chloride and silver nitrate make what?
Silver chloride and sodium nitrate.
Yeah, silver chloride and sodium nitrate. Silver chloride is special. What's special about silver chloride?
Isn't it like flashing?
No, it doesn't flash. It's insoluble. It's going to form a precipitate. Yeah. So this forms a PBT. So this is the precipitate that we get. And what they did was they analyzed the precipitate. How much precipitate did they get? They got 2.056 grams of precipitate. Where did this precipitate come from? This precipitate all of it came from the sodium chloride here, because we're adding excess silver nitrate. And so, based on this, this is what we can do. We can figure out how much sodium chloride was in there. The sodium nitrate didn't react. And so sometimes the sodium nitrate, this is called other stuff. The other stuff doesn't react. So we'll just do some stoichiometry here. So we're going to go from grams of A, 2.056 grams of silver chloride, to moles of A. I don't want to calculate, even though silver chloride is easy to calculate, just rather look it up. 143.32. 143.32 grams silver chloride per mole. So grams of A to moles of A to moles of B. In this case, we want to know how much sodium chloride is in the mixture. We can't tell how much sodium nitrate is from this reaction, but we can tell how much sodium chloride there is, because it's going to be a 1-to-1 mole ratio. 1 mole of sodium chloride for every 1 mole of silver chloride precipitates. And then we can figure out the molar mass of sodium chloride. again, I'm just going to look it up. Which you can do on the homework to save time. On the test, unfortunately, you have to calculate it. 58.44 grams per mole. Okay, so got 2.056 divided by 143.32 times 58.44. Point 8383. 8383. Allowed 4 6 pigs, so I'll carry one extra. 5 grams of sodium chloride. And so if you look at it, this is 1.6, this is about 0.8. About half of this mixture was sodium chloride. Can you see that? The total mixture is 1.6 or 16, and that's 8. So about half of it. What we can do is we can go back here and calculate it. The percent sodium chloride in this mixture is equal to the grams of sodium chloride in the mixture divided by the total mass of the mixture, 1.6240 grams of mixture. The grams of sodium chloride we just calculated over there, 0.83835 grams of sodium chloride per 1.6240 grams of mix times 100%. I have to write that in here. Oops, I just deleted that. 0.83835 divided by 1.624 times 100. 51.62. If it's 51.62% sodium chloride, what's the percentage of the other stuff in the mixture? Yeah. And so the other stuff is equal to 100% minus 51.622%. It's 48.3. I'll just do 48.38% other stuff. Well, what is the other stuff? In this case, the other stuff is only sodium nitrate. In more complicated mixtures, you might have other things in there as well. And so the other stuff is going to be this. So it's going to be 51.622% sodium chloride and 48.38% other stuff, which is sodium nitrate. In this case. Sometimes we don't know what the other stuff is. All we have to know about the other stuff is that it doesn't react. And as long as it doesn't react, then it's invisible in that sense. All right, so this is figuring out the percentage composition of mixture. And this is the same thing. 88 is the same thing. Figuring out the percentage composition of mixture. In this case, the mixture is this. A researcher dissolved 1.382 grams of impure copper. Impure copper consists of pure copper and other stuff. Do they tell us what the other stuff is? Here, they don't tell us what the other stuff is. And so we just have to call it other stuff. But what we need to know is that the other stuff doesn't react. Okay, so of impure copper, So they dissolved this in nitric acid to produce copper 2 nitrate. The solution then went through a series of steps in which the copper 2 nitrate was changed to copper 2 hydroxide, then to copper 2 oxide, and then to a solution of copper 2 chloride. This was treated with an excess of soluble phosphate, precipitating all the copper in the original sample as pure copper 2 phosphate. The precipitate was dried and weighed. Its mass was 2.637 grams. Find the percentage mass of copper in the original sample. And so for this particular problem, which is 88, we have another mixture. And this mixture is going to have copper in here, plus other stuff. And altogether, we have 1.382 grams of this mixture, which we call impure copper. The impure copper is going to go through a bunch of steps and eventually ends up at this copper 2 phosphate. And we end up with 2.637 grams. But the problem is we don't have all the equations. And there are a whole bunch of equations here. So how can we do this stoichiometrically? The way we're going to do this stoichiometrically is this. We're going to have to assume that every single copper atom that was originally present here ends up here. That is, there were no copper atoms lost to side reactions over here. And so if I started off with 1 gram of copper here, then I'm going to have a total of 1 gram of copper here inside the copper 2 phosphate. And this is going to allow us to figure out how much copper there is. So here, we assume all copper ends here. Therefore, for every mole of this, we must have had 3 moles of copper to begin with. So there must be 3 moles of copper for every 1 mole of copper phosphate that formed. So in other words, if I have 3 moles of copper in my original mixture, all that copper ends up in copper phosphate, and therefore I can have this mole ratio here, 3 to 1. All right, why don't you try figuring out the percentage copper in this mixture?